Hi class, in our last lecture we introduced new topics such as solubility product, which is our equilibrium constant for things that are dissolving, KSP, and our molar solubility, which is solving for X, which we calculate down here at the bottom of page 45. So today we're going to continue with an example with magnesium hydroxide. So in example 3, in a saturated solution that is in contact with solid magnesium hydroxide, the concentration of magnesium ions is 1.31 times 10 to the negative fourth. What is the solubility product for magnesium hydroxide? So the solubility product we are solving for is KSP, our equilibrium constant, and what we're given is the concentration of magnesium ions at equilibrium, which ends up being our solubility product. So here's the reversible reaction of magnesium hydroxide solid dissolving into its representative ions in aqueous. So our product, our reactant, magnesium hydroxide, is a solid and doesn't have a concentration, and our products do. There's a coefficient in front of hydroxide, so it ends up being 2x at equilibrium relative to magnesium's x. So what is given to us is the concentration of magnesium ion at equilibrium, which is 1.31 times 10 to the negative fourth molar, which is equal to x, which is equal to molar solubility. If we were given the hydroxide concentration at equilibrium, that would be 2x, and we would actually have to divide by 2 to isolate the x term, our molar solubility. But in this example, we have magnesium 2+. The hydroxide concentration is then equal to 2 times that, which is equal to 2.62 times 10 to the negative fourth molar. We then solve for our solubility product, KSP, which is equal to our magnesium ion concentration times our hydroxide concentration squared, since it has a coefficient of 2, which is equal to 1.31 times 10 to the negative fourth, times the quantity squared, 2.62 times 10 to the negative fourth. That ends up giving us a KSP of 8.99 times 10 to the negative 12. This means that magnesium hydroxide is not very soluble. So the whole point of calculating a solubility product is to give us an idea of whether or not the salt in question, magnesium hydroxide, is very soluble or not, since our KSP is just equal to our concentration of our products. It's very small, which means that we do not have a lot of ions in solution. Next, we're going to introduce the idea of the common ion effect. So consider an equilibrium of acetic acid CH3COOH in water. Here's the structure of acetic acid. We abbreviate acetic acid, as I just mentioned, CH3COOH. It dissolves and reacts with water, to form acetate and water's conjugate acid, hydronium. The equilibrium constant is given, which is 1.75 times 10 to the negative fifth. Again, anytime that we are using an equilibrium constant for things that are in solution, I'm just going to call them KEQ. Sometimes you may see it as K sub C, which is the concentration. This situation is actually an acid-base reaction, so you could also call it Ka, which we'll get to later in the semester. What would happen to the equilibrium if sodium acetate were added to the mixture? Sodium acetate has the following structure, formula, which is sodium ion and acetate, the conjugate base of acetic acid, CH3COO minus. That is a common ion to the equilibrium that's in question. It is present in both of our compounds. It's present in sodium acetate, and it's present in our equilibrium as the conjugate base of acetic acid. So it's present in equilibrium reaction as a product. So what happens? We are increasing the amount of product, so we must have a shift left in order to reach equilibrium. So we have a shift towards the reactants. In this situation, we've dumped in a whole bunch of product, and we are at a pre-equilibrium situation. So we have a Q, which is equal to products over reactants, that is larger than K. So when you have a situation where Q is larger than K, it must shift to the left towards the reactants in order to reestablish equilibrium. In our next example, we're going to look at silver chloride and sodium chloride. So in which direction would the equilibrium of silver chloride dissolution shift if sodium chloride were added to the mixture? So as a reminder, we have silver chloride dissolution. That is enough information to get this entire equation, because we have silver chloride solid dissolving to form silver ion aqueous and chloride ion aqueous. So the word dissolution implies that silver chloride is a solid, and it's dissolving to form aqueous ions. So that's this entire equation just from those two words. The reverse reaction, where you have the aqueous ions coming back together to form a solid, is called precipitation. Sodium chloride is added to our reaction. Sodium chloride is incredibly soluble, so it doesn't even get a reversible reaction arrow, it just has a forward reaction. So we form simply sodium ion and chloride ion. Chloride ion is a common ion to our equilibrium, and then that means we are adding more product, which shifts the reaction back towards silver chloride. So what effect does adding a common ion have to solubility? The solubility of AgCl decreases as a result of precipitation. So that is always going to be true, because for precipitation reactions, or dissolution reactions, our reactant is a solid, so we can never add a common ion for a solid which is not in solution. So our reactants are always going to stay the same. So common ion would always be adding a product, which always causes a shift back towards the reactants, which are solids, which is a precipitation. In our next example, we're going to calculate the molar solubility, which is the same as saying we're calculating X, for aluminum hydroxide AlOH3 in a 0.015 molar solution of aluminum ion Al3+. So we're going to cross out aluminum nitrate, and we're just looking at the aluminum ion Al3+. The KSP of aluminum hydroxide is 2 times 10 to the negative 32. So if you just correct that typo, we can continue. So aluminum hydroxide solid is at equilibrium with aluminum ion and hydroxide ion aqueous. Our aluminum hydroxide solid reactant does not have a concentration. We have a 0.015 molar concentration of aluminum in solution at the beginning, and we have no concentration of hydroxide. So aluminum goes up by X, and we end up with 0.015 plus X at equilibrium. And for hydroxide, we have 0 that is increasing by 3x given our plus 3 or our 3 coefficient in front of hydroxide. So we get at initial 0 plus 3x for a change and at 3x at equilibrium. So our KSP for this situation can be described as the concentration of aluminum ion times the concentration of hydroxide ion cubed, given that it has that coefficient. So we would write this expression as 2 times 10 to the negative 32 is equal to the expression 0.015 plus x times the quantity 3x cubed. But we're going to actually see if we can take a shortcut where we can ignore x. So on your next page for notes, on page 48, you may want to write down these steps on page 48 to see if you can avoid the quadratic. So in any situation where you have an expression that's the number plus or minus x, if x is less than 5% of that number, that x is a negligible amount and can be skipped, which usually helps you avoid the quadratic. This does not apply if x is alone or if x is being multiplied, like 2x. It usually works with very small equilibrium values. So let's return. We have an arithmetic expression of an addition where we have 0.015 plus x. So that's the x that we could try to skip and see if it's negligible. And 0.015 is our number from the notes page. 3x cannot be skipped because it is not part of a plus or minus expression. So we set x is equal to 0 and we move on. And we say the 2 times 10 to the negative third is equal to 0.015 times the quantity 27x cubed. That comes from our quantity 3x cubed, because 3 cubed is 27 and x cubed is x cubed. 1.33 times, then we divide both sides by 0.015, and we get 1.33 times 10 to the negative 30 is equal to 27x cubed. We divide by 27, and we get 4.93 times 10 to the negative 32 is equal to x cubed. And we take the cube root of this number to get 3.7 times 10 to the negative 11 is equal to x. So test, is x less than 5% of our number? So x divided by number times 100 is going to be equal to our percentage. Our x value is 3.7 times 10 to the negative 11. Our number is 0.015 times 100 is 2.47 times 10 to the negative 9 percentage. So yes, our x is significantly smaller than 0.015. So it's considered a negligible amount because that number is so much larger than it. In example 6, we're going to calculate the molar solubility of aluminum hydroxide in a solution where hydroxide is present at 0.01. So that should be 1 times 10 to the negative 2 molar. The KSP of aluminum hydroxide is 2 times 10 to the negative 32. So we can set up our ice table. But this time, for hydroxide, we have a beginning concentration of 1 times 10 to the negative 2 molar. That's going to increase by 3x to give us 1 times 10 to the negative 2 plus 3x at equilibrium. So we could set up our KSP, which is equal to x times the quantity 1 times 10 to the negative 2 minus 3x. So that 3x can be considered negligible and tested because it's part of a plus. It doesn't matter that there's a coefficient in front of that x. So we set 3x equal to 0 and we move on, and we say that 2 times 10 to the negative third is equal to x times 1 times the expression 1 times 10 to the negative 2 quantity cubed, which is equal to 1 times 10 to the negative 6x. And we divide by both sides, we get 2 times 10 to the negative 26 is equal to x. And we can test, and we discover that our x divided by our number times 100 is equal to 2 times 10 to the negative 22%. Yes, it can absolutely be skipped. This usually works with very, very small KSPs. Anytime you have a negative exponent for your equilibrium constant that is double digits, you could probably test this. In our next topic, activity, we are going to find out what happens to an equilibrium when you start increasing the ion concentration to a really high concentration. So, when each of the following are added to a mixture of solid magnesium hydroxide in water at equilibrium, what happens to the amount of solid magnesium hydroxide? So here's our reversible reaction. So if we were to add magnesium chloride, what would happen? Magnesium chloride dissolves to form magnesium 2 plus ions aqueous and chloride ions aqueous. That magnesium 2 plus is a common ion to our equilibrium of interest. So what ends up happening is you are increasing the concentration of magnesium 2 plus, which is a product. A shift then happens towards the reactants. The result, we have an effect on magnesium hydroxide of decreasing its solubility. Because whenever these ions are coming together and shifting to the left, they're forming a solid, which is crashing out of solution as a precipitate. So the result of a common ion is the solubility decreases and precipitation increases. What happens if we were to add calcium nitrate to our magnesium hydroxide solution? Calcium nitrate solid dissolves into 1 equivalent of calcium 2 plus ion and 2 equivalents of nitrate. Neither of these are common to the 2 products of our magnesium hydroxide, so there's no change. However, turns out if we added a high concentration of calcium nitrate, the solubility of magnesium hydroxide would actually increase. And here's why. That has to do with ionic strength, which is a measure of the total concentration of all of the ions in solution. As the ionic strength increases, there is more interaction with polar solvent molecules, which decreases the overall interaction between the ions. So what does this mean? So consider adding a whole bunch of calcium nitrate, which dissolves into forming calcium ions and nitrate ions in solution. So I've drawn them as really large just so that there's a whole bunch of them. And we have different parts of water molecules interacting with the ions. So the protons of water interacting with the negatively charged nitrate, and we have the relatively polar water having oxygen of water interacting with the +2 ion of calcium. So the whole solution becomes really sticky as you have a whole bunch of ions. And with all of these ions present interacting with the solvent, the hydroxide and the magnesium can't reform and can't bind together to form the magnesium hydroxide. So again, we're looking at this reaction. So if all of those ions in solution are preventing the magnesium and the hydroxide from coming back together, they can't form the solid and they can't precipitate. That has a domino effect of essentially increasing the solubility because everything's kind of stuck at the product side in solution. So to recap, when we increase our total amount of ions concentration, the ions are less likely to bind together. So you have more in solution, which results in less precipitation, and by extension, an increase in solubility because all the ions are in solution. Here are the factors that affect ionic strength, and we're going to describe ionic strength mu with the following equation. Mu is equal to 1/2 the sum of the concentration of component A times the concentration of component I times the square of the charge of I. So mu is the ionic strength, large sigma is the sum of, C sub I is the concentration of component I, and Z sub I is the concentration of component I. So how do we use this? So first, let's take a look at what happens when we have an aqueous solution of calcium nitrate, where 8 times 10 to the negative third molar is equal to our calcium ion concentration. So we have calcium nitrate solid dissolves to form calcium 2+ and 2 equivalents of nitrate. So the calcium ion concentration is given. I think there's a little bit of a typo here, but the calcium ion concentration is 8 times 10 to the negative third molar. The nitrate ion concentration is 2 times that amount, so 2 times calcium gives you 1.6 times 10 to the negative 2. So we can calculate ionic strength. Mu is equal to 1/2 times the sum of each of these components, the concentrations times the charge squared. So first we're going to look at component where I is equal to calcium. So for calcium, we have its concentration, C, is equal to 8 times 10 to the negative third molar. Its charge is 2, so there's our 2, and we square it. So that's just C times Z squared. For our next component, nitrate, we have our concentration is 1.6 times 10 to the negative 2. Its charge is -1, so its Z is -1 squared. When you bring all this together, our value inside the brackets is going to be equal to 0.048, and our ionic strength mu is 0.024. And next class, we'll see what happens when we calculate ionic strength.